Yes. Hello everyone. So previously we were discussing about the number systems and uh, till now we have discussed about natural numbers, we have discussed about integers, and we have discussed about a Cartesian plane of integers where there are discrete points on a plane at integer coordinates. So all these fall under countable infinite sets. Things we count. So in this set, there's a very important numbers that we haven't talked about yet, and that's the rational number. You all know what is a rational number, but to repeat, rational numbers are the numbers which can be represented in the form of a by b, where this is the division sign and a and b are integers. So any number that can be written in this form is a rational number. That is, whatever number you can get by dividing two integers. You pick two integers at random and divide them, and what numbers you get are rational numbers. Now, there are obviously few rules, which is one is b cannot be equal to 0. In fact, you can also cover all rational numbers if you don't make all a and b as integers, just make all a as integers and b as natural numbers, then b as natural numbers, then also this set is complete and you will get all your rational numbers in, and additionally you don't have to talk about b not being equal to 0, uh, because natural numbers don't consist of 0. That uh, and also you will see that many numbers can be represented in multiple ways. For example, you say you take a as an integer, you say you have -1, that's a, and b is, for example, 2, so you have -12. But this same thing can be represented also as this or as this. You have multiple ways of representing irrational numbers. So if you just want to have a definition of a set which includes these numbers for only once, not repeat these numbers, then you have to also include a definition of coprime. So you need to add the definition of coprime. What is the coprime? So coprime is that a and b cannot have common factors. Cannot have common factors. What do I mean by that? It's very simple. What I mean by that is they should not be divisible. They both should not be divisible by anything other than 1. They both I mean like both of them should not have the same factors. For example, this -1, this -1 is divisible by 1, and this 2 is divisible by 1 and 2. So since common factors is just 1, uh, then it's this is an acceptable definition of a rational number if you include the coprime parameter. If you check for -2 and 4, -2 has factors 1 and 2, and this has 2, 1 and 2. 2 is a couple of times, so uh, So you see they have a common prime factor, which is 2, and thus they are not co-prime, so this will not come into the picture. And similarly, minus 50 and 100 have a lot of common factors, and they also cannot be included. So that's the modification you can make if you want to include a rational number only once. So I should mention here, cannot have common factors other than 1. 1 will be a common factor for everyone. So yes. So this is the set of rational numbers. It makes it this complicated definition of rational numbers makes it very difficult to represent it like we had represented natural numbers and integers. For natural numbers and integers, we could write it in this curly braces, and for natural numbers, we can simply do this, and it's a very easy representation of natural numbers. But for uh, rational numbers, that representation becomes a little bit difficult. So it is very difficult to see already how will it fall, or if it will fall under this countable infinite sets, because you need to count rational numbers, and if you cannot represent it properly, then how will you count? So we will, for that, it's very simple. We will actually follow the strategy we used when we counted the Cartesian plane of integers. So we will write the rational numbers in the same way as we wrote in case of this Cartesian coordinate of integers. So how's that? Let's first write 0 by 1. And so instead of, this is also like a Cartesian product. You see, it's also integer by integer. So this is, if a and b are both integers, then these are both integers. So so this is also a collection of numbers of a and b. The rational numbers are also collection of numbers of a and b. So there's a lot of similarity between this Cartesian plane of integers and rational numbers. So we try to write this rational numbers in the same way we wrote the Cartesian product of integers. So 0 by 1. Now 1 by 1 and minus 1 by 1. So you see these are all integers actually. Anything divisible by 1, these are just integers that I'm writing right now. Minus 2 by 1 and so on. Okay. So I can write 0 by 2. It's actually not important to write 0 by 2, but I can mention it, or I can skip it as well. So let's skip it, because 0 by 2 is basically 0. So no need to write it again. Here I can write 1 by 2. Here also I am skipping 1 by minus 1. So what I am doing is I am having this modified definition of rational numbers, where a is integer and b is natural number, so that I don't have to encounter repeated rational numbers as often. I will still get them, because it's very difficult to include this co-prime definition inside this representation, but I will try to avoid as much as I can. It's 1 by 2, 2 by 2. You already see that there is a repetition, but to maintain a systematic representation, I have to live with it for now. I will let's see how I will avoid it when counting the rational numbers. How I will avoid it. So it's 2 by 2, so on. And here you get the pattern. It's 1 by 3, and then 1 by 4, and this is also 1 minus 1 by 3, 2 by 3, and so on. This list goes on. And as we previously followed the spiral counting technique, we will use exactly that. So we'll keep on attaching or labeling these rational numbers using the natural numbers. So this is the 1. We move this way, it's 2. We move this way, it's 3. Then we'll continue the spiral, where the zigzag pattern. This is the 4, this is 5. But as we are doing this, what we will also do is, as soon as we label this 2, we will try to eliminate uh, uh, every rational number which is exactly this, 1 by 1. So for example, if we multiply 2 to both numerator and denominator, we get 2 by 2, and we'll remove this from the list. If we multiply 3, uh, we get this 3 by 3, which will be here, and we'll remove this. So we will keep on multiplying this natural numbers. You see, these are other natural numbers other than 1. So we multiply 2 and remove this, multiply 3 and remove that, to get rid of any duplicates. And we continue our count. So this is 5, this is 6, and this is 7, this is 8, 9, and this is not 10 because this we have already cancelled. We go to here, 10, and you see, exactly in the similar way, we can assign a natural number to each and every rational number. So this is also a countable infinite set. And like all countable infinite sets, it has the same number of elements as natural numbers. So number of rational numbers, this is equal to the number of natural numbers. This is almost unreal because when you think about rational numbers, there are so many of them. Even if you think between 0 and 1, how many rational numbers are there? This will be infinite. You if you just simply keep on dividing by 2, if you simply keep on dividing this by 2, like 0 and 1, these are rational numbers, this is half, this is a rational number, this 1/4 is a rational number, and so on. If you keep on dividing, you will get rational numbers. In between this, you get a rational number, you get 3 by 8 here, you get 3 by 4 here, and so on. There are so many rational numbers in just 0 and 1. This itself is infinite. And again, these infinite you can also prove in a very similar way. I will leave it up to you to do this. In this similar way of arrangement, you can prove the number of rational numbers between 0 and 1 is also infinite, which is also a countable infinite set. And this is also equal to the number of natural numbers. So not only are rational numbers equal to the number of natural numbers, a subset of rational numbers, rational numbers between 0 and 1, is also equal to the number of natural numbers. And it is very counterintuitive to think, because you see, it's a very small set of numbers we are talking about now, of rational numbers that we are talking about, but both of them have equal number of elements, and that is only possible because in both of them there are infinite and countable elements. Okay, but still we have other numbers which are not rational, which are not rational because they do not fall under this definition of rational numbers. uh, of We cannot represent it as a division of integers, and so uh, those numbers will be a non-rational number or irrational number, and irrational and rational numbers make up this this whole line, which is called the real numbers, that will come that we will see in some other video. Uh, but yes, there are other numbers which are real numbers which are not rational, and you already know how to represent rational numbers. So, but what are some examples of rational numbers that you will come across daily? What are the rational numbers? Uh, so, anything like an integer, 1, 2, minus 3, something, is a rational number. Any decimal place, integer, 1.2, 2.5, minus 3.678. If it stops here, any decimal number which has a finite place of decimals, then it's a rational numbers, because you see this last number that I wrote, you can represent it like this, where both of them are integers. Now, if there are common factors, you can always separate them and write the more simplified forms and etc. But still, these are examples of rational numbers. Not only that, if you have repeating decimal places, if you have repeating decimals, those also fall under the rational numbers. So earlier I talked about only the decimal places which stops after a certain point. Like after this, there are just zeros. So there are no other digits after the third place of decimal, fourth place, or even if it stops after a million places of decimal, if it stops and the rest are zero, then also uh, that is a rational number. That what happens if it does not stop? If the decimal place goes on infinitely, for example, 0.3333, and goes on in such way. This is often represented using this bar over the top of 3 to signify that 3 is repeating. So this is also a rational number. You can also represent it like this, 1 by 3. This 1 by 3 is repeating decimals. Any other, for example, a lot of decimals are repeating. Suppose you have something like 4, 5, and then you have this repeating sixes. So you can represent it like 0.456. Wow. So this is also rational, and something where multiple places are uh, repeating. For example, you have something like this, where all this whole thing keeps on repeating. So this is 1 by 7, and this is still a repeating decimal place. This is a rational number. So repeating decimals and finite decimals. So these are the finite decimals. They fall under the category of rational numbers. But still, even after that, there are non-repeating infinite decimals where the digits run to infinity, and never can you stop at a point and say the rest, everything that comes after it is zero, and it's non-repeating. You can never find a repeating decimal places. Even after a lot of decimal points, you will never find a repeating decimal places. So those are non-repeating infinite decimals, and there are very famous examples, like for example pi. This is 3.1415 and so on. It goes on, and never does the digits repeat themselves. This is irrational. So these are irrational, and these will fall under the real numbers. And root 2, for example, a square root of most non-perfect square integers will fall under this category. Square root of any non-perfect square fall under this category. And other like e with the golden ratio 5, there are so many other numbers that are not special like this, but are non-repeating uh, decimals will fall under the category of irrational. And we will see how we can attempt at counting them, but if we can count them, and how will we classify the number of irrational numbers that are there in our real number line. Okay, thanks.